Okay, so this is a video on dilations and similarity in the coordinate plane. A dilation, spelling, there we go. Dilation, D-I-L-A-T-I-O-N, dilation is essentially a mapping. It's a transformation. So this is like kind of back in the transformations unit. And what we do is we take some object, right? And then, let's draw that a little better. Some object, and we take a point, okay? And then we use some number k. Okay, and we draw out, let me bring out the ruler for this. I'll make it a little neater. We draw out rays from that point. To the vertices of that object. And then what we do is we do a little bit of measuring here, right? So whatever distance this is, let's say k is 2, then we double that distance. So like there's 1 times the distance, there's 2. Once the distance, 2. Once the distance, 2. So we just do a little estimating there. And I'm going to bring back my ruler. And let's kind of push those lines back in. So there's 1, 2, 3. So the image, right? So let's say that this was A, B, C, and this is A prime, B prime, C prime. So ABC would be the pre-image. This is the image. What we end up with is we end up with like a larger version of it. So if the absolute value of K is greater than 1, we're going to get an expansion. Okay, so this is what we're going to call an expansion. If the absolute value of K is less than 1, then we get a contraction. All right, so if I did this again with something less than 1, my dilation would have ended up like back here, and this would have been like A double prime, B double prime, C double prime, and I would have gotten something smaller. So this point here, I'm going to call it O, is what's called the center of the dilation, okay? This is the pre-image, right? We have that language from transformations. And this one out here is called the image. Now, what makes this different from the other translations that we, or transformations that we did, translations, reflections, rotations, is that this is definitely not a isometry. These are not congruent figures. So, in fact, we're going to prove in a moment that what you get from doing a dilation is actually similarity. Okay, so if I take the figure and dilate it over this center, and this letter K, this is what we call the scale factor, right? So that's straight from what we've done earlier with similarity. But this gives us the idea that we're either making it bigger or smaller, and we're going to end up with similar figures. So let's actually, that's a theorem that we have to prove. So let's actually do that. Okay, so our theorem states that dilations map triangles onto similar triangles. Okay, so let's build a drawing here and then use that drawing to kind of explain what we're working on here. So let me build a triangle here. I'm going to build 3 points. Okay, I want to be a little more cautious about that third point. We'll put it down here, like, there we go. All right, let's get rid of that garbage. And I'm going to do this a little more cautiously. So I'm going to use the ruler here to make this work. So there's one side of my triangle, right? There's the second side of my triangle. And let's move this around a little bit. And there's the third side of my triangle, right? So we're going to call that A. Oops, get rid of the ruler. Call that A. We'll call this B. We'll call this C. So we're going to perform the dilation. So this out here is O, right? So bring my ruler back and actually do a dilation here. So I have to extend over C. Let's make a little dotted line there. Extend over B. Make a little dotted line there. Extend over A. Make a little dotted line there. And then kind of eyeball to where this is going to be. So like if that's once, this is twice. That's once, this would be twice. This is once, this is going to be twice, right? So get the ruler back out and build the resulting triangle here, right? So that one goes there. That one, whoop, yeah, it's there and there. Maybe we'll make this one orange. There we go. There. There. And there, right? There we go. All right, so let's call this one A prime, B prime, C prime. Okay, so we want to prove that these two triangles are in fact similar. Okay, so because this is a dilation, I know that OA prime is going to be some absolute value of K times the length of OA, because this is like, in my world here, this is twice as long, but it could be any K, right? So OB prime has to be K times as long of OB, and OC prime has to be the absolute value of K times OC. Okay, so the second thing here is that I've got like the fact that if I'm looking at this in the right way, in each of these, there's like 3 sets of, what do you call it? Similar triangles here. So like this red one is similar to the big red one, right? Well, we're going to try to prove that. This blue one here, so OBC, is similar to the big blue one out here. And finally, we'll make it purple. Like this purple one is going to be similar to the big purple one out there. All right, so if you kind of think about this, all the angle O's, the big purple angle O, the red angle O, and the blue angle O are all congruent to each other. So the red angle O is in both of these triangles, the blue angle O is in both of the blue triangles, the purple one is in both of the purple triangles. So I'm going to clear out some of the clutter here, and I'm only going to deal with the red pair of triangles, okay? Because the argument is exactly the same for the blue and the purple ones. So let's just clear this out and let's look at the red one. That angle O is in both the triangle OAB, and it's in the triangle OA prime B prime. All right, so let's get that there. All right, now I know here that I have proportional sides, right? So OA is to OA prime there, as OB is to OB prime, okay, because that's in these two statements. So I have proportional sides, the angle between them, so I know that triangle AOB has to be similar to triangle A prime OB prime B prime, and that's by SAS similarity. Now, likewise, triangle let's make it what I use the blue ones for, BOC has to be similar to triangle B prime O prime C prime. And what was the purple set of triangles, we're going to say that triangle AOC had to be similar to triangle A prime O prime C prime. All right, so all three sets of triangles that we dealt with there proved to be similar by the SAS theorem. Okay, so what does this mean? Well, if I look at this, AB is in the red triangle. AB has to be proportional to A prime B prime. Okay, so AB has to be the same as A prime B prime. Okay, BC was in the blue triangle, so BC has to be proportional to B prime C prime. Finally, AC has to be proportional to A prime C prime. So we now have AB proportional to A prime B prime. We have BC proportional to B prime C prime, and AC proportional to A prime C prime. So if this proportion sets up, I've now shown that this triangle and this triangle are similar by the SS similarity theorem. And that's our goal, is to say that the dilation maps triangles onto similar triangles. It mapped ABC onto A prime, B prime, C prime. So when I do a dilation, I end up with a similar triangle. Okay, so some corollaries that we get from this. Okay, so first corollary. If these triangles are congruent, then the dilation maps an angle onto a congruent angle. So if I get similarity, the angles have to be congruent. So that's pretty straightforward. Nothing unusual there. Number two, dilation with scale factor K maps a segment onto a segment that is K times the length. That's because the scale factor determines the proportionality, so that's going to work out. So that's a direct result of what we just proved. And finally, if it works for triangles, it's going to work with any polygons. And in fact, dilations map polygons with area A onto similar polygons with area k squared times a. And that's a result of what we talked about in the last set of notes, where because I have a scale factor that goes from a to b, then the area ratio has to go from a squared to b squared. So if I've gone from 1 to k, I have to go from 1 to k squared. All right, so that's the whole gist here. Basically, the upshot is that dilations map things onto similar figures. The angle size is preserved, but the side length is multiplied by k. The area is multiplied by k squared. All right, thank you.